there's some more easy properties now that we can talk about concerning determinant. Here's the first one. The determinant of a triangular matrix, so that's either upper triangular or lower triangular, is the product of the diagonal entries of that matrix. Wonderful little result. And a short version of the proof is this. We're just going to do cofactor expansions along the first row for the case of a lower triangular matrix. It would be a little different. For upper triangular, you'd use the first column. So we're going to consider the lower triangular case. So we're going to do a cofactor expansion along that first row. Now let's see what that would look like. So here is an approximate picture of a lower triangular matrix. So keep in mind we have diagonal entries. I'm going to call these D1, D2, etc. Dn, the last diagonal entry for an n by n matrix. And we have a whole bunch of other stuff down here, but all zeros up here. So taking the hint from what's indicated here, we're going to do a cofactor expansion along the first row. All right, well, here's our first row. Notice that the entries in our first row are D1 and then a bunch of zeros. Right, so I can write down, using the cofactor expansion, I can write down what the determinant of this matrix is. We'll call this matrix A. The determinant of A is D1 times the determinant of the 11 minor plus a bunch of terms that include a factor of 0. So it'll be, 0 times the 1-2 minor, and then this 0 times the 1-3 minor, and then this 0 times the 1-4 minor. But they're all being multiplied by 0, so I don't even really have to write them down. Okay. All right. So now let's think about, well, what is that M11 minor? Is this matrix? Well, it's what you get when you cross out that row and that column, and we have another diagonal matrix. So we've reduced the question of understanding the determinant of an n by n lower triangular matrix, lower triangular. We've reduced that to the question of understanding the determinant of a n-1 by n-1 lower triangular matrix. So you could turn this into a recursive, a mathematical induction argument, and in a mathematical induction argument, we would observe that, well, if it's true, if the statement in question is true for the n-1 case, can you show that it's true for the n case? And in this case, we do have that. If this determinant here is the product. Let me color code better. If this determinant here is the product of these diagonal entries, then this formula says the determinant we're looking for is that times that, and therefore that the determinant we're interested in is also the product of the diagonal entries. Okay, so it's a very nice little proof. Okay. All right. Special case of this. Note that every diagonal matrix is a triangular matrix. In fact, every diagonal matrix is both upper triangular and lower triangular. And so, determinant is the product of the diagonal entries, just as in the previous theorem. Okay. Now, there's a geometric point of view you can take on this second theorem, thinking of diagonal matrix. Let's think about the 3 by 3 case with positive diagonal entries. So looking at this matrix, well, the determinant of a 3 by 3 matrix, we have a geometric point of view on that, and that is you take these column vectors, and take those column vectors. Those column vectors are that, and that. and you look at the box, at the parallelepiped, that is, in this case it's a box, that's defined by those vectors, and the absolute value of the determinant is equal to the volume of that parallelepiped, in this case box. Okay, well, with these being positive entries on the diagonal, this determinant is positive. It's ABC, the product of three positive numbers. This volume is positive. So what we have is that in this case, the determinant is equal to this volume. Well, here is it very natural to see why ABC is an expected answer, because this box, the volume of this box is clearly ABC, product of the diagonal entries. So it's very natural and believable in this case. So now this is just a geometric interpretation. This doesn't count as a proof. For one thing, this geometric interpretation we've just made only applies to the 3x3 case. Our theorem is for any, no matter how big your square matrix is, any size square matrix. So this is absolutely not a proof of the result, but it's a nice way to think about it, a nice way to sort of visualize the result. Okay. All right, another nice fact. If you have a matrix that has a row or a column that's all zeros, the determinant of that matrix is 0. Easy to prove. Just do a cofactor expansion along that row or column. Here we go. Suppose we have a matrix A, and suppose, oh, I don't know, let's say that this row is all zeros. Right, we have all kinds of who knows what up here, all kinds of who knows what down there. And if you do a cofactor expansion along a poorly chosen row, such as that one, or perhaps such as that column, then you have a bunch of arithmetic facing you. But we're allowed to choose any row or column we want. Let's choose cleverly that row, and note that our formula then becomes that the determinant is equal to, well, it's a summation of, as we move along this row, the entry of the matrix times, and then, well, the corresponding cofactor, but, well, who cares, because it's being multiplied by 0. So all of these terms are zeros. We're adding up a bunch of zeros, and the determinant is clearly 0. So an easy little proof. There's a geometric interpretation of this as well. Now, again, I emphasize this geometric point of view that I'm about to show you is not a proof. This, again, is only in the 3x3 case. In that 3x3 case, suppose we have, let's say, these 3 columns, and here we're saying, let's say the third column happens to be the 0 vector. Right? Well, this determinant is going to relate to a volume. It's the volume that you get when you take the 3 columns, 1, 2, and 3, right? That third column being the 0 vector. And these 3 vectors together, when you make a parallelepiped out of them, they make a flat parallelepiped. It doesn't have any volume. The volume is 0. And so, not surprising, very natural to think of why then the determinant ought to be 0.